Hi everyone, welcome back to physics. Today we will start with our new topic, energy. Now, what is energy? Energy sounds like something we all use, like electrical power, or the energy it requires for you to stay awake. And well, you feel drowned of energy, you are all tired. But what is energy? We can't define energy without defining work. Okay, so first let's get to the chase of what is work. Work by definition is the application of a force over a distance. Okay, the force that is moving the object, because well, if you're applying a force over a distance, by definition, the object should be moving. Okay, now this force is always the parallel component to the intended distance or travel. So if you're pulling with a force F like this, we want only the parallel component. Why? Because the perpendicular component will never make it move in the intended motion. Imagine that you want to move the object to the right. Okay, if you push it downwards, well, there's no way you can make it move it to the right. Okay, that's why we only care about the parallel component. Parallel to what? To the intended distance, to the intended direction of travel. Okay, so if you want to move it in the horizontal, we care about the horizontal component. And as we all know, the way we get the horizontal component of any vector is with the cosine of the angle. Now, the force is a vector, but when we calculate the work is a scalar. Okay, it can be positive, negative, or zero. You can have positive work when you make something go faster. You can have negative work when you make something go slower, or you can have a zero work when you make something, well, not accelerate nor decelerate. So the velocity becomes constant. Okay, as I just said, a force applied perpendicular to the intended motion always does zero work, because well, it's simply impossible for you to make the motion. Now, assuming that the intended motion is to the right, we can have these values. The angle between 0 and 90, which is to the right, okay? We will have positive work making the velocity increase, okay? We can have an angle of 90, making no work at all, or we can have an angle that is bigger than 90, smaller than 180, going to the left. Now, if your intended motion is to the right and you are applying work to the left, the only thing that you will do is to decrease the velocity. Okay, so long story short, work is the application of a force over a distance. The only component of the force that generates the work is the parallel, not the perpendicular. Okay, positive work, you make an object increase its velocity. Negative work, you make an object decrease its velocity. Zero work, you do not change the velocity at all. So the velocity becomes constant. Now, having defined work, now we can get back to energy. Okay, now, according to the force that is being applied are the different types of energy. Okay, it can come from gravitational force, from the speed of the object, from stored energy in springs, heat, lost to nuclear energy. There is a lot of ways of having energy. Okay, but something remains constant, the law of conservation of energy. The law of conservation of energy states that energy is not created nor destroyed, it is only transformed. Émile du Châtelet in the 1700s was the first one to propose the law of conservation of energy. Okay, that was actually before Lavoisier proposed his law of conservation of mass, which is mass is not created nor destroyed, it is only transformed. For around 300 years, well, actually 200, because it was at the end of the 1700s. For around 250 years, we thought that they were independent laws. But then we have Einstein with E equals mc squared, and we found out, well, he explained why energy and mass were actually the same thing. It's like both sides of a coin. Well, doesn't really matter. That was just a fun fact. Coming back to the law of conservation of energy. Energy is not created nor destroyed, it is only transformed. The force is the agent of the transformation. Energy is the measurement of the change, and work the method. The units are joules, thanks to Joule, a British physicist. He's the one who proposed the first law of thermodynamics. It has to do with energy. That's why the unit is in his name. Okay, 1 joule is simply the energy required for moving an object with a force of 1 newtons for a distance of 1 meter. Okay, in simple words, energy is just the capacity to do work. As long as you can do work, you have energy. As long as you are applying or doing work, you have energy. So let's get to a simple example. You are pulling an object with a rope, making an angle with a horizontal of 60 degrees with a force of 3 newtons for 10 meters. How much work is done on the object? Well, pretty straightforward. The force is 3, the distance is 10, the angle is 60 degrees. So we just apply the formula. FD times the cosine of the angle. Force 3, D10, cosine of 60, we get 15 joules. Do not forget the units, please. Now we can talk about potential energy. What is potential energy? Potential sounds like something that could be, but it is not yet. Wow, we went full philosophical. Well, no. Well, yes, actually. Potential is arises from things being in positions they don't want to be. For example, 2 electrons near each other, they have the same charge, so they want to repel, but if you keep them together, they're just like jiggling to go away. Compressed springs, if you can imagine a spring and you compress it, it wants to, it just wants to go away, right? The ball at the edge, a ball at the edge of a tabletop, well, it just wants to fall and go to the ground. 2 magnets, when they have opposite charges, they want to be together, but you're holding them. So they just are like, oh boy, I want to be together. Or if they have negative, the same charge, and you put them together, they're like, I can't stand this other guy. I need to go away from it. Okay, so they don't like to be there. And they're like fighting to be elsewhere. Okay, independent from motion, it arises from the object's position. Okay, it is stored energy. Okay, if you let go the spring will just go away. If you move a little the ball will just fall. If you let the electrons that are together free, if you set them free, they will go in different directions. Okay, so that energy is just stored and it can be later retrieved into kinetic energy that we will be talking about later. Potential energy can be denoted as P sub index E, okay, potential energy. I don't like it that much. So in our class, we will be using U, okay? From now on, this U will be potential energy, okay? The ball on the tabletop, it's an example of gravitational potential energy. Look, potential energy is the U, gravitational, this sub-index G will mean that it is, that we're talking about gravitational potential, okay? Are there any other types of potential energy? Yes, they are. For example, compressed springs, they will have elastic potential energy. Magnets that are together, they will have magnetic potential energy. And there are a lot of different types of potential energy. Right now, we will begin with gravitational potential. The sub-index is G. Let's look at an example to get the formula. Assume a ball of 2 kilograms is at top of a table that is 1.5 meters above from the floor. How much potential energy does it has stored? Okay, we have that the mass is 2 kilograms, the distance that you are moving it is 1.5 meters. Now, the direction of the intended motion, well, would be up and down. Okay, now, what is the force that is generating this motion? Well, it's gravity. Gravity is the one that makes it, that is pulling it straight to the ground. Okay, so another way of saying gravitational force is weight. Okay, so we can say that the work done by gravity, okay, is the force of gravity times the height being the distance that you're moving it. So mgh, okay? If we calculate the work done by gravity, it would be 2 times minus 9.8 times 1.5. 1.5 means the height, 9.8 acceleration due to gravity, and 2, well, the 2 kilograms, okay? But in order to lift the ball, someone should perform the 29.4 joules of work. Okay, so we say that the change in the ball's gravitational potential energy is actually moving the ball upwards. Okay, so this is work done by gravity equals to the potential energy equals to mgh. This is the most important part of this slide. Potential energy equals to mgh, g being positive. Okay, that's why the minus, but that's why the negative here, because in this case g is positive. Why? Because in order to have the potential energy stored, well, someone or something has to move it upwards. Okay, another way of thinking about it is work is a scalar, so we don't really care about the direction. Okay, now that we know that potential energy arises from the position of the object, we get to kinetic energy. Kinetic energy arises from the motion of the object. Kinetic has the same root word as kinematics, kinema, motion. So moving objects, kinetic energy. Okay, now I will explain where the formula comes from. Okay, this is only for you to know where the formula comes from. We can use big for number 4, which is v squared equals to VO plus 2 times acceleration times final minus initial position. Okay, but we know that the initial velocity is 0. And from Newton's second law of motion, we know that F equals ma. I will write it here on the top. F equals ma. We can solve for a. Okay, and we would have that a equals to F divided by m. Okay, and we can substitute this a here. So we would have that v squared, we cancel this because it's 0, equals to 2 times F over m times final minus initial position. Okay, now final minus initial position is just a change in displacement, another way of saying distance. Okay, now this is 2 times F times D, but F times D is work. So we can change it like this, and then we can solve for F times D, and we would have 1/2 mv squared. Long story short, kinetic energy equals to 1/2 mv squared. This is the most important part of this slide. Okay, kinetic energy equals to 1/2 mv squared. Now, what is the kinetic energy of a ball? 4 kilograms that is moving at a speed of 30 meters per second. And we just apply the formula. The mass is 4 kilograms. The velocity is 30 meters per second. And we just used 1/2 mv squared, 1/2 m being 4, b being 30. We apply this in the calculator, we plug in the numbers, 1800 joules. So far we already know that potential energy and kinetic energy are two things that work together. How? Well, by the conservation of mechanical energy. In the definition of potential energy, we said that it was stored energy that it can be later on retrieved as motion. This means that you can retrieve the potential energy in the form of kinetic energy. Okay? The sum of these two things is called total mechanical energy. You can think about it as the energy available of the system. Okay, so all the energy that you will have available is whatever you have in kinetic, in the motion, plus whatever you have in potential. Okay, the addition is the total mechanical energy. Another way of thinking about it is, imagine that you have 300 pesos in the bank, okay, and 200 pesos in cash. Okay, you can make use of the 200 pesos in cash, okay, or you can make use of the 300 pesos in the bank. In total, you have 500 pesos. Well, the mechanical energy works pretty much the same. It is the kinetic energy plus the potential energy. We will begin neglecting resistance, air resistance, friction, and all non-conservative forces. Okay, so we can state that the energy at the beginning equals to the energy at the end. Okay, so a summary of what we've seen so far. We've seen that energy can be in many ways. Two of these are potential energy or kinetic energy. The potential energy, we will begin with gravitational potential energy, use of index G, which the formula is mgh. Later on, in another video, we will see how to apply elastic energy. But The other formula for potential elastic, it has a sub-index S of spring, is 1/2 kx squared. We will talk about this later. Also, we can have kinetic energy in 2 or more forms. This is just an example, linear or rotational. Linear, we use 1/2 mv squared. Rotational, we use 1/2 I omega squared. For this topic in specific, we will be using gravitational potential and linear kinetic. Okay, those are the two most important for this lecture. Okay, now let's get to the core of the topic. Consider a 2-kilogram object initially at rest falling from the top of a 10-meter building. What is the velocity at the half and at the end of the path, neglecting a resistance? Okay, so for this, we need to make a frame of reference. The frame of reference will tell us where, at which position, the potential gravitational energy is 0. Okay, this is the lowest position that the object can ever be. Okay, the lowest position of this object in this specific case is, well, at the end of the 10-meter building. So we have this h, okay, this h will be 10. The lowest position is 10. Now, in order to understand, well, let's make some couple drawings. At the beginning, it is at the top. Then it is asking us when it is at the half. So I'm doing the drawing when it is at the half and when it is at the bottom. Okay. Now, let's see what's going on. At the top, it is not moving because it is initially at rest. So at the top, all the energy that we have is just potential energy because there's no kinetic energy at all. When it is at this point, at the half, well, some energy is potential energy, some other energy is kinetic energy. And at the end, just before it hits the ground and it bounces or it breaks or it happens, whatever it had to happen, just in the instant that it is touching the ground, at that position, all the energy is just kinetic energy. Okay, so at the highest position, we said that there is no kinetic energy. So we can get the potential energy. The potential gravitational energy is mgh. M is 2 kilograms. G is 9.8. Remember that in this topic, it is positive. And the height, h, is 10. So we just plug in the numbers in the calculator and we get 196. Okay, so the total mechanical energy would be E equals K plus U. Okay, K being 0, U being 196. And then this is all the energy available that we have, 196 joules. This is as if I'm telling you, I have this money between the bank and cash. At the top, everything is in the bank. There's nothing in cash. At the bottom, everything will be in cash. There's nothing in the bank. Okay, in the middle, well, we will have some part in cash, some part in the bank. Okay, now if we use physics terms, at the top, we only have potential energy. At the bottom, we have only kinetic energy. At the middle, everything that is in between, we will have a combination between potential and kinetic energy. Okay, so I just moved a little this so I have space to work. At the top, here in this first position, we said that E equals K plus U. K is 0. We only have U. So the mechanical energy is 196. Now, this mechanical energy will be the same everywhere. Okay, so at this position, E equals K plus U because energy is not created nor destroyed. It is only transformed. We will be using the same E, 196, and now we will solve for V2. Okay, V2 being the velocity at the half of the path. Now look how the height changed. Okay, the height instead of being 10 meters, now it's 5 meters. Okay, substituting the values and plugging a little into the calculator. E is 196. 1/2 times 2 is 1. That's why this V squared divided V2 squared is going here alone because 1 times V2 squared is V2 squared plus 98. 2 times 5, 10 times 9.8, 98. Then you pass this subtracting to the other side and you take the root of that and we get V2. V2 will be the square root of 98, 9.9 meters per second. Now at the bottom, we do exactly the same again. E equals K plus U. we substitute the values. Now height 3, well, it is at the very bottom, so the height is 0. Okay, the mass is still the same for both of them. The energy, the available energy is still 196. We take the square root of that, and we get that it is 14 meters per second. Well, this is a pretty simple topic. Energy is not that complicated. Okay, I hope you enjoyed the video. And remember, all the questions that you have, please ask them during the class. The most important part about the videos is that you work out problems with the video. Okay, if you try to watch the video independently, it's not a good idea because you will get distracted and you won't understand. It's better, way better if you are practicing with the problems at the same time as you solve the exercises. Well, it's a pleasure to have you here. Good luck until the next time.